Hello class, welcome back to Crystallography. This is lecture number 5 and chapter 3 in Introduction to Material Science. And when we left off with our last lecture, we had just finished the stacking sequence, the ABC for face-centered cubic and the ABAB for hexagonal close-packed, our two close-packed crystallographic configurations or crystal structures, excuse me. There's one point I'd like to go back to, and we're seeing it here with ionic crystals. I had not made it very clear what the rules were or what the general trends were for cation versus anion size and coordination number for ionic crystals, which you're going to see a lot of in ceramics. And so I wanted to do a quick recap of that just so that you understood the general trends. And so I'm back on our lecture slide 19 showing the cesium chloride and the sodium chloride structures. And again, with the cesium ion being in an 8F hole, so it has an octahedral, has an 8-way, 8 coordination number of 8, and the sodium atoms are in 6F holes, and so those are octahedral holes, basically, surrounded by 6 atoms that makes an octahedron. And the general rules for cation radius in an ionic crystal is a larger cation will allow more anions to surround it. The limit is really on the low end. The anions and cations need to be basically in contact with one another. If the cation is so small that the anions can't effectively touch it on a circle diagram, then you're getting too much charge separation. You're actually having a little bit of too much negative charge. The anions effectively can't see that cationic charge. So basically the smallest cation that you can put in any given interstitial or hole in a crystal is a size such that the anions would all be touching. Just touching. You can obviously have a bigger cation but not a smaller one. So that sets a lower limit on coordination number, a lower size limit on the cation would be an upper limit on coordination number. So bigger cations will tend to have larger coordination numbers effectively. Smaller cations, smaller coordination numbers. And that generally follows the same kind of rule that we'll see with lattice strain for neutral interstitial solutes. But just wanted to clarify that, and of course it makes a good trend here. We can see that cesium being lower on the periodic table, another row down from sodium or a couple rows down. It's coordinated by 8, whereas sodium is only coordinated by 6. So bigger cations, higher coordination number, requires a bigger hole. So we'll go ahead and skip back to where we left off before with coordinates in crystal systems. Finding your way around a crystal is a lot like finding your way around a Cartesian grid system, because that's basically what it is. There are 3 different basically quantities that we would worry about in a crystallographic system. One is a point, or the location of a point. So you might want to say, where is this corner atom? What would be the point coordinate of the center of that atom, or maybe the center of a hole? You might want a point coordinate to say that's exactly where my solute atom is in this tetrahedral hole somewhere, for instance. So point coordinates in crystallographic systems are basically just the Cartesian coordinates, assuming you're starting at the origin and moving in a vector direction, x, comma, y, comma, z, and expressed just so. So let's see if we can pull up some pictures. We have 0, 0, 0 at the origin. Our axes are A, B, and C. It's a cubic system, so A equals B equals C, right? So point coordinates for the unit cell center, we would go up 1/2 A, go over 1/2 B, and go up 1/2 C. So if this were a BCC crystal and I wanted to know what the point coordinates were for that center atom in the middle of the BCC unit cell, I would say the center of that atom is at 1/2, 1/2, 1/2. So that's a point location. And if this were a face-centered cubic and I wanted to know the center of the face-centered atoms, again, 1/2, 0, 1/2, and the other remaining 5 are the coordinates of the face centers. where those atoms are. So just Cartesian, basic Cartesian coordinates for points. And of course, here on the other point there being 1, 1, 1. Okay. In addition to a point, you can look in terms of a direction. And crystallographic directions they're a lot like points. They assume that you start at the origin and move in a vector direction. So if you remember your unit vectors, I hat, j hat, k hat, you basically make an I hat, j hat, k hat, x, y, z vector starting at the origin and going to your point of interest, and that becomes a crystallographic direction. So you will need to reposition your vector to pass through the origin. So you might have to move it over one unit cell or another. But remember, unit cells repeat. They're all the same. So indexing something over by one unit cell direction, A, in the case of a cubic crystallographic system, doesn't make any difference. So we're going through the steps here. 1, you reposition your vector if necessary to pass through the origin. You read off the projections in terms of unit cell dimensions, and the projections again, that's your x, y, z, or your I hat, j hat, k hat vector directions. And this will, if you're not working in a cubic system, A, B, and C will be different. So you'll read it off in fractions of the unit cell dimensions. So 1 in the x direction is A, 1 in the y direction is B and C. A, B, and C won't always be the same if you're not in a cubic system. So it's fractions of your lattice parameter. Then you're going to normalize to the smallest integer value. So if you are drawing a vector from the origin to say 1/2 A, you'll end up going through and just dividing by 1/2 so that you have everything expressed as an integer and enclosed in square brackets with no commas. So that's different than the points. So if you see just numbers surrounded by commas, you know somebody's talking about a position in a crystal. Where's the center of this atom, or where's the center of that hole? If you see brackets, you know somebody's talking about a direction. So think linear, like maybe what is the packing in that direction? Or a dislocation might be moving in that direction, or I want to deform the crystal in that direction. So that's square brackets. So here's an example. 1, 0, 1/2. That's a vector, and you can see it indicated with the little sort of pink vector with a circle at the end of it. It's pointing 1 lattice parameter in the x direction, none in the y, and 1/2 in the z. And it just came up there with the example. So I would normalize that by dividing through by 1/2, so everything's an integer, and I would express that vector direction as 2, 0, 1, but I would take out the commas and put square brackets. So that is a 2, 0, 1 direction. If this were simple cubic, that vector direction would land me right in between two atoms that are along the cube edge. It would probably land me between atoms in a BCC system. Probably an FCC too. So let's look at -1, 1, 1. And that also came up. So thinking about it, just going through the steps, I'm going to move from the origin, I'm going to move 1 lattice parameter in the -A direction. I'm going to move 1 lattice parameter in the y direction and 1 lattice parameter in the z direction. And that is actually the backwards pointing orangish vector with a circle at the end. Don't have to normalize, but there is a convention for negative. Rather than using a negative sign in the front of the integer, you put a bar over the top. So that indicates you're going in the negative direction. Families of directions are indicated with kind of the triangular brackets and those are specific to a crystal system. So if you would encounter the same types and number of atoms going in any one of a number of directions, so that those directions are equivalent in terms of what they encounter in the crystal system, they're part of a family. And they're indicated as such. And we can point those out as we go through different crystal systems. Okay, since we've now defined a way to express direction, one thing that we can use with an established indicated direction is calculate linear density. So this is basically the 1D equivalent to that atomic packing factor, which was the volume fraction of solid atoms to the total volume of a unit cell. But it's defined a little bit differently. There's very specific rules here, and you just need to remember what they are. So the linear density of atoms is equal to the number of atoms whose nuclei are intersected by a vector divided by the unit length of a vector. So if you don't go through the nucleus, if you don't go dead center through it, it doesn't count. So you have to, another way to say that is the full diameter has to be intersected to count as one atom. So here's an example of a face-centered cubic cell looking at the 1,1,0 direction. So just to recap, that pink arrow across the top of the box went one lattice parameter, 1A in the x direction, and then 1A in the y direction. Didn't go anywhere in the z direction, so we can put it anywhere at any z just to indicate. So you can see it went from the center of one atom all the way across another and then to the center of another. So we have 2 radii and 1 full diameter. So that's the equivalent of 2 diameters. And we will check it out by filling in our equation. So apparently this is aluminum, which we would know if we knew the lattice parameter. And we can go through and look at this in terms of atomic radius. So that's, which we don't necessarily need for linear density, but we'll need for other things. So 2 atoms in the green box. That means we've intersected 1 full diameter and 2 half diameters. The length is 4r. Okay, so real length. That's why we needed the atomic radius. So the length of the vector is 1 full atomic diameter plus 2 radii. This is because we are going in the close packed direction across the face. Knowing that it's aluminum, we know that that is 0.143 nanometers or 1.43 angstroms. And so we get a linear density of 3.5 per nanometer. So per nanometer distance in the 1,1,0 direction, we will encounter 3.5 atoms. So that is a close packed direction, in fact, which is important for mechanical properties later on. So to recap, the rule for linear density: number of atoms whose nuclei is intersected by the vector divided by the length. So how many full diameters do you intersect? Okay, which naturally brings us to the 2D equivalent, planar density. That's also important for mechanical properties. So we have the full 3D with atomic packing factor, linear density 1D, and now planar density. So planar density is calculated for a plane of atoms. So those are the faces of a unit cell or any plane that cuts it. So in this example, we're going to look at the 1,1,0 plane of iron, and we're going to look at how many atoms it has per unit area. As you can see, this is not a close packed plane. If we took the corner atoms on the unit cell that you see indicated in with the dark spheres over on the figure to the left and blew them up and just looked at them sliced straight through the nuclei, this is the 1,0,0 plane for BCC iron, for body-centered cubic. So this is not very close packed. And you can see there's our unit cell repeat, or our unit cell projection. So having calculated the relationship between the lattice parameter A and the radius of the atoms in the unit cell using the body diagonal, we know that we have this relationship between A and R. So we can use that to get the area that we're looking at there with effectively the unit cell face. So all we have to do is figure out how many atoms we've intersected on that face. And so the rule here is the number of atoms per 2D repeat unit, which in this case is 1. So in the case of linear density, we counted the number of full radii, or excuse me, full diameters that we intersect with a vector in the noted direction. With atomic packing factor, we counted the number effectively of total spheres that the unit cell intersected for a given crystal structure. For planar density, we're looking at effectively the number of circles that we're intersecting, how many full circles. So in this, you can see if you take the red box, you've encountered 4 quarter circles. So that's effectively 1 atom per 2D repeat unit, which in this case is the unit cell face. Doesn't always have to be. Not every plane is going to be a unit cell face. For instance, the 110 plane is definitely not a unit cell face. It's going across the diagonal. And then if we complete our little equation here, the blue box, the area per 2D repeat unit in this case is a squared. So we have 1 atom per a squared. And if we wanted to express that with an actual length unit, we go from lattice parameter A through the atomic radius to nanometers, so which is 0.1241 in the brown, and that gives us 12.1 atoms per square nanometer. So fairly sparsely packed plane. And we can convert that to whatever units we feel needful. Okay, speaking of crystallographic planes, how do we denote a given plane? Planes are a little bit different than points and directions in that they use a reciprocal system to call them out. This is called the Miller indices system, and it's probably a holdover from mineralogy. And the rule here is that you use the reciprocal of the 3 axial intercepts of the plane. You clear the fractions, kind of like you did with the direction, and use common multiples. And in this case, parallel planes will have the same Miller indices because effectively, right, the unit cell repeats. So another way to say this is draw the plane, look at where it cuts across each of the 3 axes, X, Y, and Z. Note that cut point in terms of the lattice parameter. A for a cubic system, ABC for a non-cubic system. Express it as a reciprocal, clear the fractions, and you're good. So here's another way of saying it in steps. You read off the intercepts of the planes with the axes in terms of A, B, and C. Take the reciprocal, clear the fractions, reduce to the smallest integer value. The notation here is parentheses, no commas. So if you see commas, you're looking at a point. If you see square brackets, you're looking at a vector direction. And if you see parentheses with no commas, you're looking at a plane. And the same convention holds with a bar. If it's a negative intercept, you use a line over the top. So here's an example. We have a system that's not necessarily cubic, looks cubic, but we don't know. So we're using A, B, and C to denote 3 different lattice parameters. A in the X, B in the Y, C in the Z. And we're looking at this blue plane. Well, it cuts the x-axis at A, which is effectively 1 lattice parameter. It cuts the y at B, 1 lattice parameter. It never cuts the z-axis. So it touches it at infinity somewhere. Now we take the reciprocal. We get 1 over 1, 1 over 1, 1 over infinity, which is 0, at least in the limit. So this is the 110 plane. So this is the plane that has close packed directions in the body-centered cubic system. This would be cutting straight through the middle of that center atom. And since we only had integers to begin with, our reduction gave us the same thing. So the Miller indices would be 110. This is the 110 plane. So we have another example here. So again, not necessarily a cubic system. So it looks like we're intercepting at 1/2, 1/2, 1/2. Excuse me, 1/2 A never hits the y-axis, so that would be infinity, and doesn't hit C. So I would call it a 200. Let's see if I'm right. It hits A at 1/2, never hits B, never hits C. I take the reciprocal, 200. No need for reduction. Not a particularly important plane per se in any of the systems we're looking at. So just another example here. Again, not necessarily a cubic system. Looks like we're hitting it 1/2, 1, 1/2. Nope. 1/2, 1, 3/4. Okay. Not good to always eyeball it. So the c-axis is hitting at 3/4, not at 1/2. It's parallax error there. So I would take the reciprocal, which would give me 2, 1, 3/4, and here we can do a reduction to get all integers. So we multiplied through to get the lowest integer value for that 4/3. So this is the 6, 3, 4 plane. We don't know what crystal system it is, other than apparently it's not cubic because A, B, and C are different. So this is 6, 3, 4 plane. And here's just an example of a family of planes that might be the same. Planar families are indicated with the curly brackets, the same way directional families were indicated with the triangular brackets. And again, ones that are families that are effectively equivalent will be dependent on the crystal system. Equivalent families in BCC are not the same as equivalent families in FCC. Okay, crystallographic plane examples. So, why do we care about different planes in different crystal systems? Are they different? They're very different. And from our standpoint, given that we are going to be looking ahead towards mechanical properties and diffusion, things like that, one of the biggest things that we care about is atomic packing. How tightly packed, how well occupied are different planes. So if we were to draw the 100 and the 111 crystallographic planes for iron, we could calculate planar densities for each one of those. We would find, and we're not going to do this here in the live lecture, we might do this as an example, but we'd find that the 111 plane was probably quite a bit more densely packed, simply because you are going through that center atom. For close packed crystallographic systems, there are particular planes that are closest packed in terms of you have each circle surrounded by the greatest number of circles it can be surrounded with as you cut through the atoms on the plane. In the face-centered cubic system, that's the 111, and again it's the basal planes on HCP. Those have special significance in terms of ease of deformation, and we'll see that, pick that up again in Chapter 5 and again in Chapter 8. So close packed directions and close packed planes. Even if it is not a close packed crystallographic system, there's always going to be a close packed direction, and that will tend to be the easiest direction in which to deform a crystal. So those are, if you know nothing else about your crystal systems, be prepared to think in terms of what are the close packed planes and directions for each one of the systems, at least that you'll encounter with metals. So, do we make generally materials out of single crystals or polycrystals? I mean, unless you're making optics or aesthetic gemstones, typically your engineered materials, ones for which you need good mechanical properties, are going to be polycrystalline, and with the smallest possible crystals you can get. So in a single crystal, because the packing in all of your different crystallographic directions tends to be different, and we just calculated a difference for iron. 110 and 111 are very different for BCC iron, right? 100 is pretty sparse, 111 is a close packed for body centered. So we would expect the properties to vary with direction in a single crystal because the atomic packing is varying. If nothing else, you're looking at a different equilibrium spacing of those atoms in each of those different directions, and wow, back in Chapter 2 we learned that equilibrium atomic spacing and the depth of the potential energy well led to all kinds of different properties. In fact, properties that are related to the potential energy well and interatomic equilibrium, interatomic spacing do vary with direction in a crystal. So even a very symmetric crystal like a cubic system will vary with direction simply because packing varies with direction. And this is a good example. This is from an excerpt from a renowned fracture mechanics text, Hertzberg, showing the difference in modulus for a body-centered cubic material. I'm presuming it's probably iron, but I don't know. So if you look in the 100 direction, if you measured the modulus of that material, and yes, it is iron, it's E edge, you would get 125 gigapascals, but if you went in the close packed direction straight through the middle, it's not quite, it's more than double. More than double. Same material, very symmetric crystal system, but because you looked at a property that was dependent on interatomic spacing, modulus, coefficient of thermal expansion would follow this same trend. If you were to heat that crystal up for a given unit temperature change, it would elongate more, probably double, in the edge direction, in the 100 direction, than it would in the 111. So it would probably no longer be a cube if you heated it and cooled it. Other properties that related to that will follow trend. So you have a symmetric crystal, but you do not have isotropic properties. Polycrystals, on the other hand, if you get enough of them together and they are randomly oriented, you can average those differences out. In this case, you're looking at an optical micrograph, photomicrograph of iron, and according to the caption, it's randomly oriented, it's isotropic, something you'd get from maybe multiple cold working and recrystallization steps, fairly equiax grains there. And it's got an average modulus, not dead on between, but it's an average across all of the different crystallographic directions. So you get isotropic properties much better from polycrystals, and it's polycrystals that are themselves isotropic. If we were to roll this and deform it such that most of the grains were lined up and oriented in a given direction, we would trend back towards the properties of single crystals, because again, you're no longer isotropic and you have the same kind of preference. And there's a picture of what you would get there. That isn't just a stretched photo. That really is a photomicrograph of something that has been probably rolled. So how do you get polycrystals? We will discuss this much more with microstructural transformations, but polycrystals are basically a result of nucleation and growth. If you are in a melt, say, the little square figure there shows little inner pink squares that represent crystalline nuclei, maybe in a melt or maybe nucleating in a solid microstructure, a new phase nucleating. They'll nucleate on high surface energy or other favorable sites, and they'll grow together, but because they weren't all oriented the same way to start with, they'll run into each other as they gobble up the parent matrix or liquid and grow, and eventually end up with grain boundaries. And grain boundaries are surfaces within a microstructure. They do not have nearly as high an energy as, say, a solid air or solid liquid surface, but they do have a much higher energy than the center of the grain, because you don't have nearly as high an atomic packing. Things don't quite line up, and so grain boundaries are, compared to the center of a grain, wide open. So they are higher energy, they have a higher void fraction in 2D, they're diffusion freeways. So if you need to diffuse something in, it will probably go in first along the grain boundaries. And these are things we'll take advantage of in especially metals processing. Polymorphism. Two or more distinct crystal structures for the same material. Water has a lot of these, especially when you look at temperature and pressure. There are a few engineered materials that are distinct for their polymorphism and for which we take advantage. Titanium has an alpha and a beta form. Those tend to be used both as themselves and in duplex. Iron is also notable, although it's distinguished by temperature. The high temperature polymorph is gamma, austenite, face-centered, and the room temperature is body-centered cubic, also known as alpha ferrite. Carbon obviously has quite a few, again, both with temperature and with pressure. And here is a sort of a 1D phase diagram showing the 3 different phase forms of iron at 1 atmosphere of pressure. Going from the liquid cooling, we get onset of solidification at 1538 C, and we solidify as a BCC structure called delta iron that will transform from body-centered cubic to face-centered cubic at 1394 degrees C, and then to another body-centered cubic not with the same lattice parameter at 912, and that's for pure iron. If you put some carbon in, those numbers change depending on how much carbon. This is specific to 1 atmosphere. Those numbers would change quite a bit if we, say, went a mile deep into the Earth. Lucky for us, most materials processing is done at the Earth's surface at 1 atmosphere of pressure. So here's another image of diamond. Diamond, it actually has a crystal system named after it, the diamond carbon system. And it's useful for a lot of things. Graphite has more of a clay mineral structure, which would look similar to a hexagonal close packed with secondary bonds, and that's why it has its lubricity and very anisotropic properties. So that is it for crystallography, kind of a whirlwind tour. There is no substitute for practice if you want to get used to Miller indices and identifying crystallographic planes and basically being able to walk yourself through at least our simple cubic crystal systems and identify close packed directions or relative sizes of interstitials, holes. You need to do quite a bit of practice on that. So I would definitely recommend homeworks. Our textbook has great problems, and if you are taking this at one of the colleges, you'll very likely have a good interactive team exercise to reinforce these principles. So stay tuned. Next time we will be taking a radical turn from the orderly world of metals and ceramic crystals and into the rather squiggly world of polymer structures. They do have a lot of similarities. They have repeat units rather than unit cells, and those do have a lot of similarities, but that's where they end, and we will learn more about that in next lecture. See you then.